friends, welcome to this video. In this video we are going to work upon multi-class segmentation using the famous UNET architecture. For this task we are going to use the Oxford IIIT Pet dataset, which consists of images of cats and dogs and their respective masks. So the mask consists of three classes and each class is represented by fixed pixel value. The pixel value 1 represents the main object, pixel value 2 represents the background, and pixel value 3 represents the border class. So for this tutorial what we are going to do is convert these pixel values from 1 to 3 to 0 1 2 by subtracting them by -1. So they will be converted like main object will be now represented by 0, pixel value 0, background with pixel value 1 and border with pixel value 2. So now let's move on to the coding part. Now we're going to write the code to extract the data from this Oxford IIIT Pet folder. It consists of image folder, which consists of images, and this annotation, which consists of try map, which consists of 3 classes. Now we also have the text files here, which consist of name of images and other thing. What we just need to do is we extract these names, this name of the name of these images. Now we have the name for the train validation and also for the test. Now for the training validation we will extract from this file, and for the test we will extract from another file. Now let's move on to the coding part and import all the required libraries. Import OS, import numpy snp, and to read those files we will import the pandas. Now let's write a function load data, which takes the path of the dataset and give us the list of all the path of the images and masks for the training, validation and testing. So we also going to split the training data into training and validation, as they both are in the same, and it's up to us how we're going to want to split them. So now let's write the path for these train val text file and the test.txt file. Test actually train underscore valid path, so it's going to be os.path.join the path, and the name is the annotations. Okay, annotations. Okay, now the file name is trainval.txt, trainval.txt. Like this we are going to write the path for the test file. Copy this from here. Instead of trainval we are going to write test. So now we have the path for the train validation file and the test file. Next we are going to write another function which take these files and give us the complete path of the required names, the images and the mask. So let's write this code first here. We're going to give us train x represent the images, x basically represent images and y represent mask. So train x consists of the list of path of the image and train y consists of the list of the path for the mask. So let's name it a process data. Okay, I'm going to give it the main path and the train valid path. Like this we're going to write for the test x and test y, process data path and test path. Okay, we need to write this function. Now we're going to write this function def process data. Now it's the, let's write data path and the file path. Okay, now here we're going to use the pandas to read those files. So the data frame df is equals to pd dot read csv. Okay, file path. Okay, the separator, as it's not a comma separated file, it's a space separated file. So separator is going to be space, and the file don't have any header value, so header should be none. So now we have the data frame, and now let's print this data frame and see what the value is. Let me comment this out. if name is equals to main, then path is equals to copy it from here, rename. It's like this. Call the load data path. Okay. Now let's run it again. And again game nothing. I don't know why. Why it should be there. Okay, so I get to know what the problem is. I put an extra underscore here. Now I'm going to run it again. So now I can see we have the data frame values. Let's ignore this till now. No, ignore this till. Now you can see we have the names in the row, in the column 0. So we need these names. Let's extract the names. Names would be equal to names is equals to data frame 0 dot values. So now let me show you names. Close this and we'll again run this. You can see we have name here in this list, names represented form full list. Okay, so now we have the names. We need the images and mask path completely. So images is equals to, so let's me run a loop here for name in names. So we have the name, individual name. Now we're going to join this name to the data path, that is this. Now os dot path dot join the data path with the proper now images. See, images, and after images it's the name what we require, name dot, and the extension of the images I think should be jpg. Okay, it's jpg. Write the dot jpg. The same thing we're going to do for the mask. Stripe equals the mask. For the mask we need the annotations less trimaps dash name dot, and let me check the extension for the trimaps. It's png. It's png. Okay, so now we have the both images and the mask. We're going to return these images and the mask. Images less masks. We have to write return here. Okay, now we have the both images and the mask for the train and valid. Now we are going to split the training into both, into training and validation, and for that we are going to use the sklearn function. From sklearn, model selection, import train test split. I'm going to use this train test split. Train x and valid x. So we're going to convert this train x into again training and the validation. Train x test size should be 0.2. So 20% images for the validation and rest 80% for the training. And the random state value 42. Now the same thing for the mask, that is the train y. Train y and valid y, and here instead of train x it should be valid x, and rest both the test size and the random state should remain the same. Now we have the training image and mask, valid image and mask, and the test image and mask. So let me return these things. Return train x kind of set format, train x to train y, valid x to valid y, and same thing for the test x to test y. So now we have this. Now let's write the information here. Let's check how many images for the test, train and valid are there. Dataset, train, train x, valid, and I am writing this code in Python 3.8 actually, I will tell you. And we have this f-string kind of format which is newly introduced. Now valid x for the test, len test x. Okay, now let me run this program again. We're going to see any problem or not. Now we have splitted the entire dataset correctly into training, validation and testing. So now we can move to the next part, that is writing the code for the UNET architecture. So let's start the code for the model, that is the UNET architecture. So let's import some layers. Let's import the model function. So first of all, you're going to write a basic convolution block which consists of two 3x3 convolution, where each convolution is followed by batch normalization and a ReLU. And after that, we're going to have the max pooling operation. So con block will be con block, not like inputs, number of filters for the convolution layer, and let's write pool as a boolean of pooling. But if it's true, then we should apply pooling, else we should not apply pooling. Now x con 2d, number of filters, kernel size is 3 and padding should be same, and as input as inputs. Next is the batch normalization, input is x. Next is we introduce the ReLU non-linearity. Okay, so we have first convolution here, and we need to copy this again, as we need to repeat the same thing, just input is going to be different. Now two convolution layer complete. Now after that, it should be pool is set to be true, then we should apply pooling, like p is equals to max pool 2d, a 2 by 2 max pooling we need to apply. Input should be the previous feature one, that is x, and if pooling is true, then we will return two things, the feature map from the convolution layer and also the feature map after applying pooling. And else if pooling is not true, then we will return only, we will only have the feature map from the activation function, the ReLU activation. So that's the convolution block, the main block which we are going to use in. Next, let's start building UNET. Build UNET should be named the function. First, shape of the input. Next, num classes, how many classes are there? As we already know, we have 3 classes. First, we define the input layer. Inputs is equals to input, it takes shape as the argument. Next is the encoder. So we're going to write the encoder here. Simple x1 p1. The x1 is the feature map from the ReLU and p1 from the pooling. So the first encoder block, simply write the con block. Input should be the inputs, and the number of filter should be for number of filter I will use not the original filter, like starting from 32 64. I will use small number of filters, as I need to train to my small system. But and also for this demonstration purpose, these smaller filter would be enough. you can increase these filter values. So first encoder block is ready. Next, for next one, copy it, and now naming should be changed x2 and p2. So x represents the feature map before the polling, and p2 represents the feature map after polling. So now the input for the second encoder block should be the feature map from the polling one, and this should be doubled. I think I will double it. Now name should be x2, x3, p3, and input should be feature map after second polling layer. Now we can change those 32 filters to 48. Again x4 and p4, and input should be the feature after polling layer 3, and this 32 can be changed to 64. Now we'll write the bridge connecting the encoder and the decoder. So bridge is going to be a single convolution block without polling. So con block, and its input should be p4. Number of feature, let's double from 168 to 128. Oh, not 168, it should be 64 to 128, and pool set to be false. We don't need any pooling here. So this, now we've completed the encoder bridge. Now we'll move to the decoder part. So in decoder we're going to upsample the feature map. In encoder what we do is, if we have image size like 256 by 256, it's going to subsequently reduce the spatial dimension, that is height and width. And the decoder we're going to perform the reverse of the encoder, that is we are going to increase the spatial dimension of the feature map. So first we need to perform an upsampling operation. We are going to perform the bilinear upsampling, a 2 by 2. So interpolation bilinear, and input should be b1, that is the feature map from the bridge, that is this. After that we perform the concatenation with the skip connection, the feature map from the encoder, the appropriate encoder feature map. Concatenate. So just make sure the shape is, this should be proper shape for that. Now I'm going to use the x4. Now let's see that we give intuitive understanding. Here we upsample, we double the spatial dimension, height and width, and we can see here no pooling is there, so size should be same, shape, that is spatial dimension of the p4 feature map and the b1 should be same, and p4 is after pooling, so before pooling we should have same dimension as that of the u1. So we'll write x4 here, and before writing this, let me make sure that the shapes are correct. So you can, what you can do is write print u1 dot shape, so it will give the shape, and x4 dot shape. Now let's call this function name main and build unit. Okay, the shape should be like 256 by 256 by 3, and number of classes should also be 3. Now let's okay, so you can see the spatial dimension, height and width are same, 32 by 32, and here also 32 by 32. Now let's concatenate both these feature map, as these have same shapes but the number of filters are different, and that's not a problem here. So we can write this concatenate 1 as u1 and x4, and after that it is followed by the convolution block, the con block. The input here is c1, feature map is 64, and pooling is false. So that is the first decoder block. Now what we can do, we can copy this entire decoder block and paste. We can change the naming u2 and c2 and then x6. Input here would be x5, the last feature map, and we are going to concatenate the u2 feature map and the x3. Yeah. Now the input would be c2, and number of filter will be changed from 64 to 48, and pooling is false. Like this we're going to write two more blocks, and X is again name change Q3, C3 and X7, and input would be X6, and we concatenate the U3 feature map from the U3 layer and the X2, and then it followed by convolution block. C3 feature map changes from 42 to 32, and pooling is false. This last decoder layer is X7 would be the input. Okay, now should be U4, C4 and X8. I think the name is appropriate. It should be U4 and X1. Now input would be C4. Okay, and it should be. So the decoder block is complete. Now we'll have the final output layer. Output would be a con 2D block with num classes as filter, one as kernel. Padding is going to be same. Activation is going to be softmax, and input would be X8. Okay, now let's going to return the model inputs and the output. Okay, the model is nearly ready. Just need to check it. Is any problem? Let's print this summary for this model. If summary is correct, then we can assure that the model is built. So you can see the model is working. Correct model. Input would be, input shape is 256 by 256 by 3 the number of channel, that is RGB format, and the output is 256 by 256 by 3, and as we have 3 classes, so its output will be 3. If we just change output to like 10, the number of output classes should also be 10, and I can see the output classes has changed to 10. Okay, so that's about the UNET architecture. Now we will start working on the dataset pipeline, and for that we are going to use the tf.data API. Let's start coding and open our data file. Let's import the TensorFlow as tf, and also import the CV2. Let's go to the bottom of the document. First we are going to write the two functions, first to read an image and second to read a mask. Read image. Okay, so it's going to take the path as x. X is the path. So we're going to use a CV2. So CV2.IamRead x CV2. We're going to read it as a RGB image. So CV2IamRead underscore color represent. I will read this as RGB image. After that we are going to resize it. Resize x to a specific width and height. Specify the width and height above. Width, height is equals to 256 and width is equals to 256. Okay, so we specified it. Now let's normalize the value by dividing the image with 255, as 255 is the largest pixel value. Now the values, now the image, that is the array, contain the value between 0 and 1, so it will normalize all the values. They are going to return it as a float 32. X is equal to x dot astype and np dot float 32 and return as x. Okay, so this is the function that is going to read the image from a path. Same function, read mask x equals to cv2 dot IamRead x. See, now you have to read this as a grayscale image. IamRead grayscale. Okay, now again we are going to resize it. So now here I will show you something. Like this, call the function here read mask and train y0. Save it, and what we're going to do is I'm going to show you something. Let's resize the image to a 16 by 16. Now I'm going to print this x 16 by 16, and we are in data.py file. So let me run this data.py file. Now I think you can see clearly this image is resized to 16 by 16. Now you can see the pixel values, that is 2, 1 and 3 you can see. So here let me show you more correctly. Let me do some more things in it, changes in it. So x, as we know, this 1 is the main object. If we main object to 0 and the background which is 2, we write 32. Okay, my mistake. Now the border x, which is equals to, if is equals to 3, then it should be 255. Okay, now see, you will see the difference, and you can see in image. So you can see that these 0 represent the main object, and around 0 you can see you have 255. So this act as the border, and background you can see the value 32. So through this this is a numerical image. You can see this array represent an image. Just thing is that it represents a 16 by 16 image. You can see other images like this. So it's an I believe it's an easy way to visualize the image. You can easily see and grasp the concept behind this image. So this 0 represents the main object, and the 255 around these zeros represent the border, and rest 32 value 32 represent the background. So this is how we're going to read the mask. As I have already told you, what we're going to do is we're going to subtract 1 from the each pixel value. Now if we just print x, we should have 0, 1 and 2 value. You can see 1 and 0 and 2. Okay, now let's again resize it to proper size, not 16 by 16. This is just to demonstrate you how the image will look, and we're going to return it as an integer 32. Okay, it should be y, it should be x, sorry, np.int 32. Okay, and we're going to return the y. Okay, so both these functions are ready, read image and read mask. Let me remove it from here. Now let's write the code for the tf data API. tf underscore data function name. It's going to receive 3 parameters. First is the in list of images path, list of mask path, their respective mask, and the batch 8. Now dataset is equals to tf dot data dot dataset from tensor slice, passing it the x and y, that is image and the mask path. Again dataset. Now we're going to shuffle that dataset. Shuffle buffer size is equals to 50,000. Let's say to 5,000, not 50,000. We don't have so much of images. Now we're going to use these read image and read mask function to read to convert that path into an appropriate array. Okay, so we're going to use map function, and here map we have to specify the name of the function. So I will specify the name of the function, but I haven't written it. Write it. The preprocess function, I name it preprocess. So let's do one thing, define preprocess below, just a blank preprocess. Okay, what it takes is the x and y and gives the array. Now let's go back to our tf dataset function. Now we have converted these path into the arrays, or you can say the tensors. Now I'm going to set the batch size. Dataset dot batch. So batch size is given in the batch variable. Now dataset is equal to dataset dot repeat. Okay, now dataset is equals to dataset dot prefetch. So prefetch will help us to fetch some batches of the, if I specify 2 and the batch size is 8, so it fetches 2 sets of the batch size 8 in advance. So now we're going to return dataset. Now it's time to write the preprocess function. Let's write another function here, f. Let's take these x and y. Let's decode this because these are in binary format, so we need to decode it. So x dot decode y is equals to y dot decode. Now image is equals to read image x, mask is equals to read mask y. Okay, I'm going to return image comma mask. Okay, as we have used numpy, we need to convert this Python function f into a TensorFlow operator. For that, we're going to use the tf dot numpy function. It should take f, the function name, the input variable we need to pass x and y. It take x and y, can see, and the data type for the output. So image mask gave a data type of float 32, and this mask is of integer 32. So we're going to specify it here dot float 32 and tf dot int 32. It returns the image and the mask. You can see the image and the mask. Now we need to convert those masks. As those masks are having value like 0, 1 and 2, we need to convert them to one hot representation. So we need to use tf dot 1 underscore hot. First is the mask, after that is the number of classes. So number of classes we have here is 3, and the return data type should be int 32. Now one more thing, we need to set the shape for those images and mask. For image it should be height, width and number of channel 3s, and for mask set shape should be height, width and number of classes, that is 3. So now it should return the image and the mask. Here this function processes an individual path and it is converted into an array here, and this array is, this whole Python function is converted to TensorFlow operation, and then we return this image and mask, and it is used in this tf data API. Now let's check this dataset, tf underscore dataset. What take is the x and y, that is image path and the mask path. Train batch size, let batch size be 8. So we'll see if it run correctly or not for x and y in dataset. Okay, we'll print this shape to check if they are working correctly. So we have batch size of 8, so shape of x should be, should be batch 8 comma 256 by 256 by 3, and that should be the shape of the mask also. Let's see if our prediction is correct or not. Data. Okay, we have a spelling mistake at the shuffle. Okay, should be 1h, not 2h. Okay, so we have an error and I know where it is. Okay, it should not be y, it should be x. I just confused between x and y here. Let's again check, and x, and everything here is x, and here also everything should be x. Now let's run it again. Okay, let me close it. Okay, now let's run it. Okay, now you can see the shape of the image and mask. 8 comma 256 by 256 by 3, 8 comma 256 by 256. Okay, so we have completed the code for the dataset pipeline. Okay. Now I'm going to use this dataset pipeline to train the model. Now we can start working on training the data, on training the model, the UNET, the Oxford IIIT Pet dataset. Let's open the train.py and start writing the code for training the model. First of all, we're going to import some libraries. Import OS. Okay, spelling mistake. Beginning only. NumPy. And again mistake. Now we'll import TensorFlow. Let's import some callback from the TensorFlow. From TensorFlow.Keras callbacks, import model checkpoint. It is used to save the model. It is used to save the model. Now let's reduce LR PLAT EAU Okay, next is early stopping. Is complete. Now we need to call some function from the data and model.py. From data import, first is load data, okay, second is tf.dataset, okay, next one is model. From model import build unit. I will pull the main. Let's first seed the environment, both numpy and the TensorFlow, np.random dot seed it on, and that's how you seed the TensorFlow random set seed 42. Now you call the dataset. We have the dataset. You can directly copy it from there and paste it here. Okay, so data is also there. Let's define some hyperparameter first. First is the shape. Shape is 256 by 256 by 3. Next, number of classes 3. Learning rate 1e minus 4. The batch size 8. Next is an epoch. Number of epoch, it will say 10. Do run it on very low number of epoch. Now we are going to shape, take, and the number of classes. Okay. Next we have to compile it. Model compile loss is equals to, as we are using a multi-class, it's a multi-class segmentation, so it should be categorical cross entropy. Now the optimizer is Adam going to use here tf.keras.optimizers Adam, and here is specify the learning. Okay, so we have compiled the model. Now we're going to build the dataset using the tf-data API. Train dataset should be tf dataset train x train y. Batch size is should be batch, not batch size. Batch is equals to batch size. Like this you can create for the valid dataset. tf data set valid x, okay, valid x, valid y, batch is equals to batch size. Okay, so we have done this. Now we need the number of iterations for the training data set, the valid data set in each epoch. Iterations, so it should be train step should be simply number of images in the training data set, train x, or we can also write train y, both are same, and the batch size divided by batch size. So there are the number of, so train steps is basically the number of batches. Valid steps is equals to number of images in the valid data set divided by the batch size. So always remember, in the train step, batch size should be what you provided with the trained data set, and same for the valid. Let's write some callback function. Model checkpoint. The model should be saved with the name model.h5. okay. Verbose, we have to set the verbose to 1 and save best only. Save the best model only. Otherwise, what's the advantage of using these callbacks if we don't save best one? This means that if the loss validation increases instead of decreasing, that they should not save the model, to save the best model, the minimum loss rate. Now reduce learning rate on plateau. the one knows where lows. Patience I, the patience should be set to 3. If till 3 continuous epoch the validation loss does not decrease, then it should decrease the learning rate with a factor of 0.1. Now let's see, right, verbose to 1 min LR, minimum LR it should achieve, and below that it should not go below minimum LR. Next is early stopping. Okay, it's basically just like if for a specific number of epochs the validation loss does not decrease, then it should stop, otherwise the model will start overfitting. Again we need monitor the matrix score here, and the number of patients let's set to 5. Verbose 2. Okay, so these are the callbacks. Now we can call the model fit function to train the model. Okay, first is the train dataset. Okay, per epoch this train step, the validation data should be valid dataset. Validation steps, valid steps, hypothesis. Now specify the callbacks. Okay, so code for training the model is complete. Let's run it and check for any error. So I think there is no error till now. So the training begins. Okay, so it's going to take 10 minutes. Okay, I think 12 to 15 minutes is going to take for this first epoch. So what we can do is still now we can write the code for that. In the test file we're going to predict the mask, compare them with the ground truth, and we can import some functions. Every is 3, then this function. Okay, and we need the dataset, the test dataset. We can copy it. So we have the dataset now. Now we're going to load the model. So model, we need the we write the code for saving the mask. Okay, so for x comma y in zip test x and test y. Okay, so let's write a progress, also include progress bar imported from tqdm, import tqdm. So tqdm is kind of progress bar which we include here. Total is equals to len test x. Okay, so first extract the name x dot split. So this extract the name from these paths. So these x and y are the path for an image and its respective mask path. So split it and split -1 here. So we're going to have the name with the extension here. Now first we're going to read the image. Read image. Let's specify one more thing. Height 256. Okay. Width is equals to 56. Inside num plus also maybe we require it. Read image. I think we can copy or import this function. Copy it. Edit from. Okay, just change the name y, mask path is y. So the shape here of the y is, let me tell you, is 256 by 256. So we have the image, the mask. We have also resized, okay, it should be 256. We have resized it. Nice, you know what we do with the mask is subtract it with -1. We can also expand it dimension here, and we do expand dims -1. Now its shapes is like 256 by 256 by. Now it's time for the prediction. Model dot predict np dot expand dimension x, and x should be 0. Right, is 0. The mask. Now we need to extract the maximum index value. So just like p is equals to np dot argmax p, x is equals to minus. So now we have the index for the maximum value. Now we will supply expand its dimension p, x is -1. Now we need to concatenate these three images: image, the mask, and the predicted mask. So now we need is the, so I will stop this as I've already trained a model. I'll copy that model. So I will train the model, this model file here, and this is not train on few, it just only train a few box, not much higher training is there. So just trained on 5 box only just before this tutorial. So what we can do is, so now we have the model also, we have loaded here. Now what we need to do is the shape for the x. Now here one major issue. So let's split the shape. So what we need to do, we need to make sure that all these three, x, y, and p, should have same shape. Okay, CV2 is not defined. Let's define it above. So you can see this. So it's 256 by 256 by 3. It's a 3 channel. There's 3,1. It has 1. So we need to make sure that every mask and image should have same number of channels and the height and width. Height and width are all the same. Just need to, let me just check for the mask. Why it is okay? I know why it is there. Should be read it as a grayscale image. Now let's go and check it again. So we now need to convert this one channel image into 3 channel image, and I know how can I do it. What we can do is we can color these y is equals to y, add them, multiply them to the num classes. Now is the main step to convert these one channel image into 3. np dot concatenate. Write y here, and x should be okay. Let's check for the y, and if it's correct, then we will do same for the prediction also. So you can see the mask shape is same as the input. We will do the same procedure with the prediction also. I think we can copy everything from here. Just change this name right to p, and p. It's like PPP. Okay, thing is correct, I think. Okay, so the problem for the shape is now solved. Now what we need to do is we need to put them together and save them. First of all, as we divide the image with 255, so it would also be multiplied by 55 to get the original image quality. convert it into in 32. Okay, now final image, what will save is np dot. Here we specify the image, first the input image I, and the ground truth mask y, and the predicted mask p. That's and the x is here. We can also do one thing, we can separate these separate this with some little space, like specifying height, width, and number of things we didn't require x dot shape. Let's do np dot once, okay, with height, width is 10 and number of channels 3, and multiply by 255. Now we can separate these things with a line, which will give it a little more clarity between these. So it can, let's create a folder with the name results. Results folder is there. Close this. Now we'll need to save this final image. Okay, first will be path result slash name. Final. Okay, let's run this function and see if there is any problem or error. Okay, we have no problem. So it's like all the input array dimension must have, axis must have same exactly. Okay, so we need to check what's the problem here with the x. One thing, and the shape, that's the good thing, because we have error in the shape. Again line dot shape, print them in the same order, and p dot shape. Let's check. Okay, it's 6 by 2. The line, let's try it without line first. It's without line, then will be good. Otherwise this line should not cause any problem. Just check it without line. Okay, we still have the error. Okay, I know what the error is. I've set this to -1, it should be 1, and by mistake I've written it -1. Now let's check. Okay, so now you can see in the progress bar it's moving, and we have some images. Let's stop it because it's going to take a lot of time. Stop it and see some sample shots. The results folder. Okay, so the predicted mask is correct, but the ground truth mask is white. So let's solve this problem. Okay, so that's the issue here. We haven't we just these are images only, not the mask. That's why it's performing like this. Let's remove all these images and again run it. So let's have some. Okay, 38 images are enough to see. You can run all the images. So see this first image, it's really nice. I believe good result is there. So first is the real input image, second is the ground truth, and third is the predicted. So you can see the predicted is really good, and in some case it's going to be even bad also. Like in this image it's little bad, in some places it's over segmentation and some places it's under segmentation. So you can train it on more epoch. I've just trained it on 5 epoch, and in 5 epoch I believe that this performance is good. It's not that bad. So like this you can see other images, and you can just see the mask on all the images, and this image is really bad. I believe there's no, you can still see the images are okay, with this performance. So that's all for this videos. I hope you enjoyed this video. If you like the content, then please share the video, like the video, and if you still have any problem or query or anything in your mind, just comment below. I will try to answer all your queries. Thank you. Have a nice day.